Good morning. Fortunately, my camera fell over yesterday and the screen broke. So for the next couple of weeks, it'll all be screen recording, screen capture instead of the actual recording. Thank God for insurance. On Tuesday, dot product. We finished up dot product. I forgot I didn't actually have to finish it up, but whatever. Today we're going to look at the cross product. Why is that text the wrong color? I have no idea what's going on with PowerPoint. That did not fix it. What's going on? If I fix you on here, does it fix everything? Of course it doesn't. I hate PowerPoint. Whatever. Two vectors. U1, U2, U3, and V1, V2, V3. Cross product. U cross V is this quantity. What kind of quantity is that? Right, it's a vector, isn't it? Cross product is also referred to as a vector product. Because when you take the cross product, the result is a vector. Whereas remember, the dot product gave you a scalar. So you don't need to memorize this. So I will show you a way of calculating the cross product. Now, it does unfortunately require linear algebra. It's a determinant that we're going to take. So we'll be looking at that method in linear algebra in a couple of weeks. So it'll make more sense in a couple of weeks. Properties of the cross product. It's no longer commutative. We say it's anti-commutative. U cross V is negative V cross U. Right. Now, notice that that's not going to change the magnitude, right? So switching the order of the cross product doesn't change its magnitude. All it does is flip its direction by pi. Right, so it goes in the exact opposite direction. That is useful to remember. It does distribute across vector addition. So same property as with the dot product. Where the scalar is for scalar multiplication doesn't matter. If you cross a vector with the zero vector, the result is the zero vector. Cross a vector with itself, you get the zero vector. And then we have a new product, the triple scalar. U dot V cross W is U cross V dot W. So this is the triple scalar product. And what it's saying is as long as you keep the vectors in the same order, you can switch the order of the dot and cross products. And the result's the same. You can't, however, do U dot V cross W. Dot product's a scalar. You can't do scalar cross a vector. Of course, as a corollary to property 3, same thing with dot product. Which is, again, a useful property to remember. We related dot product to angle between the vectors, right? We can do the same thing with the cross product. Magnitude of the cross product. Right, so the magnitude of U cross V is the magnitude of U times the magnitude of V times sine of the angle between them. Geometric applications of the cross product. Locate two vectors U and V such that they form adjacent sides of a parallelogram. The area of the parallelogram is the length, the magnitude of the cross product of the two vectors. And moving into the third dimension, you have a parallelepiped or parallelepiped. I don't remember which one it is. I think it's parallelepiped. Three-dimensional parallelogram. With adjacent sides given by the vectors u, v, and w. The volume is the absolute value of the triple scalar. And notice, because it's absolute value, the order in which you write them doesn't matter. All right, so you could do v dot u cross w. You'll still get the volume because it's absolute value. Right, the only thing that would change would be the sign of the resulting constant. One of my absolute favorite topics from physics, and I say that with all the sarcasm I can muster. Torque. Who's had introductory mechanics already? What's torque?
Force times distance times radius.
So you're giving me work, not torque.
R cross.
So I don't want a calculation. I want what is it actually?
Oh,
What does it measure?
force take it to rotate an object. Like that.
You're close, but it's not the force to rotate.
The resulting force of rotating. How is the work taken? Rotate an object.
It's the tendency of a force to cause a rotation. Torque sucks. Rotational mechanics in general is just terrible. And there are two things that affect torque. The force and distance from the rotational axis. Obviously that was very easy, right? So what happens? I'm trying to push here. It's going to require more force, right? The closer you are to the axis of rotation, the more force it takes. Which means the less tendency the same force has to cause rotation. And theoretically, if you push right on the axis, you get no tendency. You will not cause rotation. It will require infinite force. Okay? So the further away you get, the less force is required. So again, the higher the tendency of the exact same force to cause rotation. Torque is represented by the Greek letter lowercase tau. It said measures tendency of a force to produce rotation about an axis of rotation. So what we do is we let R be a vector with initial point located on the axis of rotation. Terminal point is located at the point the force is actually applied. So you can think of it as a radius. right? Radius from the axis of rotation. F is the actual force that's being applied. Then the torque vector is R cross F. But a lot of the time when we want torque, we want its magnitude. We don't actually want the vector itself. That's also why anyone has had to change their own tires. Freaking lug nuts. That's why you generally want a much longer arm, because then it makes it easier to rotate. Unless, of course, you use a electric one, which is even better. Of course, when I learned to change a tire, we didn't have electric ones. That's how old I am. I still remember the days of having to use a manual pump to lift the car up. Damn that. I think we're going to get into applications, yeah. So there is something else that's interesting about the cross product, which we can visualize right here. What do you notice about the torque vector in relation to both force and radius? It's perpendicular to both of them. The cross product is always perpendicular to both vectors. So if you remember that problem we did last time, where you tried to cheat, where we had to find a vector that was perpendicular to two vectors, we had to use the dot product because we didn't know about this yet. We could have just found a cross product. Could have just done U cross V. Now I think PowerPoint fixed it. It did. Now it actually goes to the slide that I wanted on. Show that A dotted with A cross C equals 0. Actually, there's two ways I can do this. There's a hard way and there's an easy way. Use the triple scalar property. A dot A cross C is the same as A cross A dotted with C. Any vector cross itself is what?
0.
0 vector dot with any vector is what?
Yes.
Done. Hard way, not using any of the properties. Define your two vectors, A1, A2, A3, C1, C2, C3. Now actually compute the triple scalar. Starting with parentheses. We need to do A cross C. I won't use the definition, the memorization one. Right? I'll set it up as a matrix. So the idea is what you do is you set up a 3x3 matrix and take its determinant. So that's what the absolute value bars are going to mean. The first row of your matrix are the standard unit vectors. Second row is the first vector of the cross product, the components. Let's actually give myself more room with that K. Third row is the components of the second vector of the cross product. Then we use cofactor expansion along the first row. We're looking for the I component first, the I hat. So you cross off the row and column that it's located in. The result is a 2x2 matrix. Find its determinant. Determinant of 2x2 is very easy. Take that product. Take that product, but you're going in the opposite direction, right? So it's negative. There's your I component. Minus. And the reason it's minus is clear when you study cofactor expansion and linear algebra. For now, you just have to take my word for it that it has to be minus. Now looking for the J component. Do the same thing. Cross off the row and column. You're left with a 2x2 matrix. Take its determinant. And then it's times that J hat. And then finally, you're going to want the K hat component. It becomes plus, cross out row and column, you're left with a 2 by 2 matrix, find its determinant. There's your cross product. And if you compare that to the definition, it's exactly what it is. So instead of memorizing the formula, you can also just set it up as a determinant. I love how that text stayed the same, but all the other ones are not the right color. I've got no bloody idea what's going on. All right, so that was A cross C. I'm going to switch the order for the J hat so I can get rid of that negative. And how'd you do dot product?
First term times each first term plus second.
A1, A2, C3 minus A1, A2, C3. Negative A1, A3, C2 plus A1, A3, C2. A2, A3, C1 minus A2, A3, C1. That's 0. Oh boy, I remember this one. This one's a bit of a doozy. I don't feel like working with subscripts either. So I'll use the Greek letters alpha, beta, gamma for that last one. All right, here's the question. When trying to show an equality, two ways you can do it. The first way is to fully simplify both sides and show that they're the same. The second way is to start with one side and show that leads to the second side. For that second method, it doesn't matter whether you start with the left-hand side or the right-hand side. Right, so you can start the left-hand side, work to the right-hand side, or start the right-hand side and work to the left-hand side. Trying to think which one would be easier to do. I think starting with the left-hand side is the best option. Right. Notice the wording. That means this is a true statement. So if this was on a test and you were doing the work and you didn't get equality, you did something wrong. I'm telling you it's true. Versus, I could say, does that equality hold? Then you don't know. Then you would have to actually go through the work. Right? You either have to prove it or provide me a counterexample. We're going to assume that show's not there. We're just going to look at this. First off, are both sides defined operations? Can you do a triple cross product? Yes. Right? Cross product is a vector, and you can do the cross product of two vectors. That's fine. Right-hand side. Dot product is a scalar, and then it's a scalar multiplication, which gives you a vector, and you can subtract two vectors. Do they both give you the same quantity? Right. Are they both scalars or both vectors? That's what same quantity means. Right. Left-hand side is what? Right-hand side. So they're also both vectors. So we're off to a good start. If one was a scalar, one was a vector, then you know you're done. The equality can't hold. Then you just have to provide a counterexample. So we're off to a good start. Both sides are defined, and they're both the same quantity. Now let's actually work to show that they're the exact same vector. I'm actually going to start with just B cross C. I'm not going to set up the matrix. I'm just going to do this visually. V gamma minus W beta, comma, W alpha minus U gamma. That is the best gamma I've drawn in a while. U beta minus V alpha. Notice in the second component, I flipped the order. So I just didn't write out the negative. I already distributed that negative through. Oh, this is going to be fun. It will be X times U beta minus V alpha minus, no, I'm sorry, that's not X, that's Y. Minus Z times W alpha minus U gamma. That's the first component. Second component. Z times V gamma minus W beta minus X times U beta minus V alpha. Again, I'm not setting up the determinant. It'll take too long. And it would be X times W alpha minus U gamma minus Y times V gamma minus W beta. And let's just make sure I did that right. Yes. Yes. No. Oh, I'm looking at the wrong term. Okay. Yes. 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 That is correct. I would recommend you write out the determinant until you get the hang of it. I'm able to just visually put it in column form in my head and see how the cross product is going to work. So I don't necessarily memorize the formula. I'm just able to visualize it in my head. I don't know why it always does that. I have to do Control V. I really don't get it. So I'm gonna put that up there for reference, because now the idea is we have to simplify that and get it to be that right-hand side. I guess the first thing we can do is distribute everything through. Plus CV gamma minus ZW beta plus X V alpha minus X U beta, and then X W alpha minus X gamma plus Y W beta minus Y V gamma. Distribute all that through. I'm also going to do this. This allows us, is that what I want to do? Yeah, I'm pretty sure it's what I want to do. That's what I'm going to do. Is that what I want? Is that going to work? Or did I not want to do that? Did I want to? I put the UVW in the first one? Ah, okay, I see what I have to do. I did my groupings wrong, but that's okay. That's how I want to group them. Reds are one vector, oranges are the second vector. I notice that every orange is negative, so I can factor out a negative. Then it'll be y v alpha plus 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 yes, now I'm back on track. Notice in the first vector, first two terms have a u in common. Left with y beta plus z gamma times u. Then we can factor out a v from the second terms. And a w from the third. Plus now what's happening. I may come back to this one. I'm going to do that. I'm just going to come back to this one tomorrow. See what's going on. Because I have nothing in common I can factor out.
What would happen if you group the ones with similar view?
That's what I was trying to do. The problem is there's nothing that's, all of them are going to be the same.
Yeah,
So-
there's the
Which ones?
Y, U, beta, and X.
XU beta, though, is in the second component. Right, so the grouping's going to have to be this, you have to group the same components together, unfortunately. I'm making some kind of stupid algebraic mistake, and I'll figure it out when I look at it. Show this. So first, A dot B, AB cosine of theta. So the magnitude of A dot B would just be the absolute value of AB cosine theta, right? And the magnitude of A cross B is just AB sine of theta. Right, then our right-hand side would become this. Right, the quantity of AB sine theta all squared plus the absolute value of AB cosine theta all squared. What happens when you square a quantity?
You have a variable square, the cosine square, and you have 2a.
Well, first off, a and b are both positive, right?
Yeah.
Which means a squared and b squared will be positive, so I can take them outside the absolute value. What about cosine? Cosine theta, is that always going to be positive? Will cosine theta always be positive?
Yes. It is squared.
I'm not asking about squared.
No.
But what happens when you do square it?
It will.
So I can just get rid of that absolute value altogether, can't I? Because that whole thing will always be positive. That's why we couldn't get rid of it up here. I could have pulled the AB out and wrote AB times the absolute value of cosine. But once you square it, you no longer need the absolute value. It becomes redundant. There's an a squared, b squared common. Factor it out. Sine squared plus cosine squared. Which is a squared times b squared. So the next two. I have a triangle and unit vector perpendicular to a plane. I don't have time for this one. So we want a triangle that has vertices P, Q, and R. What I want to do is start with that. Start with a parallelogram. God, that was terrible. That's better. If you cut it in half, get a triangle, don't you? Call that P, call that one Q, call that R. Well, if you look, PQ QR, adjacent sides of a parallelogram, right? So if we find the area of that parallelogram, cut it in half, don't we have the area of that triangle? PQ. I think I actually did in my notes. Not that it matters, but I did QP to keep the same initial point. Next, we're going to wind up taking magnitude anyway, so the magnitude would be the same regardless. So what's QP? We'll do it that way. Keep the same initial point for the two vectors. What was it? What's QR? And now take the cross product. -6 minus -6 for the first component. Second component, 6 minus 2. Can I do that right? No. I think I looked at. Yeah, okay, so that's not QP. That's PQ. That should be QP. -132. I think that becomes 6 minus 6. Then this would become -6 plus 2. And then -3 plus 9. Zero, -4, 6, right? Which is factor out of 2. 0, -2, 3. The area of our triangle will then be a half the length of that vector we just found. Length of 2 is just 2. 2 times a half is 1. We're just left with the length of 0, negative 2, 3, which is what? Root 13 is the area of our triangle. So I'll go ahead and take a look at whatever question it was. 2. What was it? Yeah. I am 99.9% certain that's the correct cross product. It's then just from there how I'm going to group it. I'm not 100% certain. I don't remember. So that's what I'll take a look at. And we'll finish that up on Friday, as well as look at the last problem. So first homework on WebAssign is due tomorrow. Second homework, which is on dot products, is up. It's due next week. And continue working on the first project. See you tomorrow.